So let's talk about structural isomers. Structural isomers are also known as constitutional isomers. So whether they use the term structural or constitutional, we're talking about the exact same thing. And when we're evaluating molecules to determine whether they're isomers or not, we have to follow a couple of rules that will help us determine if they are isomers or if they are different molecules. So the first thing is they must have the same molecular formula. For that, we got to make sure we know what molecular formula means, but it might be something like I look at a molecule and it has the formula C3H8O. And if I look at the second molecule, it also is C3H8O. That would be an indication that they have the same molecular formula. By having the same molecular formula, you might think that they are the same molecule, but that would not be the case. What we see is when we look at structural isomers, what's different about them is the connectivity of atoms. And so that's the requirements for a structural isomer, is that they must have the same molecular formula, but their connectivity of atoms is different. And I'll kind of highlight the second point, the B part there, because we have to see what we really mean by connectivity of atoms. So let's go by example. So here's two molecules, and we're going to evaluate them for their whether they are structural isomers or not. And so the first thing we have to do is first find out, do they have the same molecular formula? And so I can look at the first molecule here, and I can see that we have carbons in the structure. And we can look to see there is 1, 2, 3, and I'm marking them out so I make sure I don't count them twice. So I have 3 carbons. I have 1, 2, 3, 4, 5, 6, 7 hydrogens and 1 bromine. And on the second molecule, I also have, we can see very clearly that there are 3 carbons, 1, 2, 3, 4, 5, 6, 7 hydrogens, and a bromine. So with that, we see that they have the same molecular formula. The question we have to then ask is that they do have the same molecular formula. They have the chance to be isomers, but they can also be the exact same molecules. We got to make sure we're not dealing with the same molecule. So typically when we have questions on isomers, you're typically going to figure out whether they are isomers, are not isomers, or are the same molecule. And so the same molecule will have the same molecular formula and the same connectivity of atoms. Two molecules that are not isomers will not have the same molecular formula. So these have a chance to be either the isomers or they're going to be the same molecule. So let's look at the connectivity of atoms. And to help you appreciate what is meant by connectivity of atoms, I'm going to walk through it with you with this example. So I'm going to number the carbons in each structure. Carbon 1, carbon 2, and carbon 3. And then I'll do the same here, 1, 2, and 3. And you can see here, if we look at the structure on the left, the first carbon is directly connected to this hydrogen, this hydrogen, this hydrogen, and carbon 2. In the second structure, we see that the first carbon is connected to this hydrogen, carbon 2, but a bromine as well. So notice the connectivity is not the same. If it was the same, the second structure would be connected, the carbon 1 would be connected to 3 hydrogens and carbon 2, just like it is in the structure on the left. On the left, carbon 1 is connected to 3 hydrogens and a carbon 2. On the right, it is not 3 carbons and carbon 2. It is connected to 2 hydrogens, carbon 2, and a bromine. So the connectivity is different. Therefore, these have the same molecular formula. Their connectivity is different. Therefore, these are constitutive isomers, or also known as, constitutional isomers, also known as structural isomers. So these are isomers because of that. Now, another way to do this to determine if they are isomers when you find out the molecular formula is the same, instead of going through what we just went through and going down through all the carbons and figuring out if they all match each other, the other way to do it, which I think is a better way, in a way that I like to talk about it and teach people about it, is not worry about the trying to figure out what we just did there. That's the way textbooks typically talk about it. But the way I'm going to kind of talk about it as well as a better way is just name them. If they have the same molecular formula, but the names are different, they're isomers. Okay, but notice what's constant here. They have to have the same molecular formula. So let's go ahead and do that. And so I just go ahead and name them. For this, you got to be able to name molecules well, and so that's a prerequisite for doing this method. So this actually does two things. It strengthens your ability to name molecules, and it helps teach you about isomers. I have a bunch of other videos on naming these kind of molecules, so go look at that if you need some help with naming. But let's go ahead and name these really quickly. The molecule there on the left has 3 carbons, and so this is going to be parent is prop. Because it has 3 carbons. All those carbons are single bonded. So this is a propane molecule, and it has a substituent. The bromine is a substituent. It's on the 2nd carbon. And so this is a 2-bromo propane molecule. If we look on the structure on the right, it also has 3 carbons, so it is a prop parent. The family name, it's an alkane, so it has propane as its suffix, and then notice it also has a substituent, but this time it's on the 1 carbon, and so this is 1-bromo propane. And so from there you can see the molecular formulas are the same. They have different names, therefore these are isomers of each other, and in this case these are structural isomers. For those of you who are just learning about isomers, this is the first type of isomer you will learn probably in your courses, and so therefore this is the way it is done. For those of you who are kind of reviewing for a final or for the MCAT or some test beyond this, there are other isomer types out there besides structural isomers, but those have the same molecular formula, the same connectivity of atoms, and they differ in other things like stereochemistry, optical chemistry and stereochemistry differences there. I'll have videos covering that as well down the line, but realize this is one type, and this is the only type that really has the connectivity differences. Cis-trans isomers and things like DL stereoisomers, they have the same connectivity, but they differ in a different way. But for now, if you're just getting started, this is an approach to it. Let's look at a few more examples to kind of strengthen our understanding of these isomers. So I'll go, the rest of this is all just going to be example driven. Here I've drawn a third structure on here, and the question is this an isomer of the other structures? So again, for that, the first thing we want to do is make sure it has the same molecular formula. Again, I see 3 carbons, carbon 1, carbon 2, and carbon 3. I see 7 hydrogens, and I see 1 bromine. So there's that. And then I'm going to go ahead and name it and figure out if it's the same or different. So once again, being 3 carbons, all single bonded, we're talking about the prop family or parent name and the alkane family name, and so that's propane. And I got a substituent, the bromine, on the 1st carbon, so that's a 1-bromo propane. So in this case, this is the same as now the structure in the middle because they have the same molecular formula and same name. Those 2 molecules are actually the same, even though you might think, well, wait a minute, that bromine's at the bottom in the middle structure and at the top on that 1st carbon in the one on the right. But we just went ahead and named it, and we see that they have the exact same name. And so when you compare this one to this one, these are the same molecule. If you compare that one to the first one, these are isomers, and more specifically, structural isomers, because they have the same molecular formula but a different connectivity of atoms. Let's take the 2 that look the same and just kind of walk through how we can also recognize that the connectivity is the same. And one way to do that is notice if we look at carbon 1, we see that carbon 1 is connected to 2 hydrogens, a bromine, and carbon 2. In the middle structure, it's connected to 2 hydrogens, a bromine, and carbon 2. You just said the same thing twice. 2 hydrogens, bromine, and carbon 2, they both connect to the same thing, therefore the arrangement is the same. And if that's still a little bit confusing, again, that's why I go to just go ahead and name it. If you name it correctly and they come up with the same name, you will get the same, you're dealing with structural isomers. The reason they're the same is because, and it's hard to do in a two-dimensional space as we have here, but the carbon bond between carbon 1 and carbon 2 can rotate freely. And so if you rotate that freely, notice the bromine will actually move from one position to the other position as you rotate it. And so that's why they're actually in the same. These molecules that we look at, when we look at organic molecules, they're not fixed in space. They move an awful lot. They change their shapes, so to speak. And we'll talk more about that in the next slide when we look at a few more examples. Okay, so here's a common question one would get, and it's which of these are isomers of butane? And I have drawn the structure of butane at the very top and labeled it butane, and then I have 5 structures below that we'll look at individually one at a time. It's not that one of them is the right answer. This is not multiple choice. This is A an isomer of butane? Is B an isomer of butane? Is C an isomer? So these are individual comparisons between butane and the ones below. So what I would do is pause the video, give it a try, and see if you can figure it out, and then come on back and I will go through each of the structures one by one. So the first thing you need to really do is figure out, well, the first order or the first thing you need to do to determine whether they're isomers is figure out, do they have the same molecular formula? Well, I better figure out what the molecular formula of butane is first. Since I've drawn the structure here already in the problem, we can do that. And so if we look at butane here really quickly, we can see that it has 1, 2, 3, 4 carbons, which is expected because but is a parent for the number 4. So it has carbons, it has 4. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is C4H10 is the molecular formula of butane. So let's now go look at A, and we'll look at A first all by itself. And so what I'm going to do here is just make sure it has C4H10 as a molecular formula. If it is not C4H10, I know it is not an isomer, and I'm done. So let's take a look. So we look at 1, 2, 3, 4. So there are 4 carbons, and if I count the number of hydrogens, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so they have the same molecular formula, so that passes the first test for whether they're isomers. The next one is the connectivity the same, or the other way to do is I'll just name it, and if it names something different than butane, then I have myself on my hands an isomer. And so with this one, I see that there's 4 carbons. So when I'm going to name that A, it's but. They're all single bonded, so the family is ane, and there's no substituents. So A is the same as butane. It is not different. They are the same molecule. Now, you might look at that molecule and go, wait a minute, but it looks different to me. It looks like, if you look at the carbons, it looks like it's making the shape of an L on its side, where in the structure I've given to you, all the carbons are in a row. And what these are basically different conformations of the molecule. We didn't break any bonds here. If you go through the arrangement of them, and I'll do one as an example, because remember, the second rule is basically, are the arrangements different? If they are, they're isomers. But if you look at carbon 1 in both structures, carbon 1 is attached to 3 hydrogens and carbon 2. And that's the same in both the structure A and the butane structure given in the question. If you go on to carbon 2, we see that carbon 2 is attached to carbon 1 and carbon 3 and 2 hydrogens, and that's the same in both molecules. The best way to describe this to you, and if you go on to carbon 3 and carbon 4, you'll see that the connectivity is all the same with both of these molecules. So these are actually the same structure, even though visibly to our eyes they look a little bit different. And that's why I give you, encourage you to name them, and if they come up with the same name, it's the same molecule. So what you can think about this is think about you. Think about you being, in this case, butane, or you're a molecule. Notice sometimes you're standing, sometimes you're sitting, sometimes you're laying down, sometimes you're doing a yoga position. They're all you. You haven't changed. You haven't broken any bonds. You're not any different. You're the same person. You're just in a different shape and time, right? And we change our shapes all the time. These molecules do the same. They bend and turn and change, and that's what you're seeing here. The molecule given looks very straight, like almost like it's laying down, where the one in A looks like it's bending over, like maybe trying to pick something up off the floor, where carbon 1 is the leg, and carbons 2, 3, and 4 are the trunk and head of the body, bending over to pick something up. So the arrangement, the connectivity of the arms, the head, and the legs is the same in both. They're just in different conformations, different positions. Let's go on to B, and if you want to give B another try, pause the video, give it another try with the new information, and then come on back and we'll go through B, the structure in B. Now I erased A just to give me a little bit more space, but we go ahead and we can number these carbons and go ahead and first figure out what is the molecular formula of this. And you could number it this way, or you can number it the other way. Again, for this point, it doesn't really matter. What I get is C4, and then I also get H10. So once again, the molecular formula is the same as the butane molecule given in the question. And so we're off to a start. So we passed test 1 for isomers. Test 2 is the arrangement the same, and for that I'm going to go ahead and name it. It's got 4 carbons, and so that's a bute. Its family is an alkane, so that's ane, and there's no substituents, so this is again butane. Again, it's just another conformation of butane. In this case, it looks like it's standing up with its head bent over or bent down. Maybe a way to think about it, but again, it's all connected, still the same. Let's go on to structure in C. So in both A and B, the structure was the same. So they weren't isomers, they were the same molecule. Let's go to C. In C, I'm going to go ahead and number the carbons. 1, 2, 3, 4, 5. So that's C5. Well, right there I can see that's not the same as the one given. There's already 5 carbons in this molecule. There's only 4 in butane. So right off the bat, I know that these are not isomers. I can just stop right there. They have to have the same molecular formula, and so C is not an isomer of butane. What about D? So for D, let's go ahead and get the molecular formula. So 1, 2, 3, 4 carbons. So it's got C4. And then for hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, I get 10. And so there's a chance that this is an isomer. So let's go ahead and name this one. So to do that, I can see that this is an alkane. So it ends in ANE. I find the longest continuous carbon chain in that molecule. That's 3. And so 3 is prop. And then I have so I've numbered 1, 2, and 3. So that's the 3 carbons that I have numbered 1, 2, and 3 as being my carbon chain. And then we have this group hanging off of that chain, and that's a methyl group. And that methyl group is on the 2 carbon. And so this is named 2-methyl propane. And so this is not got the same name as butane. They have the same molecular formula, but they don't have the same name. And so these are isomers of each other. So 2-methyl propane and butane are isomers of each other. They have the same molecular formula, but the connectivity is different. And so you can see that connectivity different in carbon 2. look at carbon 2 in the structure given and the carbon 2 in D. I'll kind of highlight where one of the main differences is. So if you look at carbon 2 in the structure given in butane, you'll see carbon 2 is connected to carbon 1, carbon 3, and 2 hydrogens. In D, carbon 2 is connected to carbon 1, carbon 3, that's the same, but it's also connected to carbon 4 and only 1 hydrogen. So the arrangement of the atoms is different amongst them. And so these are isomers of each other. Let's go on to structure E. I'll number the carbons 1, 2, 3, and 4. And we can see that it has 4 carbons, and if we count up the hydrogens, 3, 6, 7, 8, 9, 10, we get the same molecular formula as butane. Now the question is, does it have the same name as butane? So I can see that the family is an alkane, so I put ane in. The longest continuous carbon chain is 4, so it's butane. So the 4 carbons, notice they're all connected together, and then the hydrogens, there's no substituents, so this is butane we're staring at in E. This molecule is doing some yoga position, but it really is the same molecule as we see in the structure given. The structure given is sort of laying down, it's straight, all the carbons are kind of connected in a row straight across the screen, and in E it's kind of doing some zigzag pattern, but they're still all 4 connected together. So again, if you just want to look at connectivity really quickly, if you look at carbon 2 in the structure in structure E, carbon 2 is connected to carbon 1, connected to carbon 3, and it's also connected to 2 hydrogens. That's exactly what we see in butane in the structure given. Carbon 2 is connected to carbon 1, carbon 3, and 2 hydrogens. Connectivity is the same. And to do connectivity appropriately, you should go through all 4 carbons and prove to yourself that each of the carbons in E and each of the carbons in butane are connected to the exact same atoms. Yes, they don't visibly look identical, but again, that's why we don't go off look, we go off naming, we go off looking at connectivity to see if they are exactly the same molecule.